Uh, uh, Hello everyone. Today I'd like to talk about BBCube 3D heterogeneous 3D integration to provide terabyte per second bandwidth with lowest bit access energy for AI HPC application. The demands for high data bandwidth between CPU, GPU, and memories increasing in emerging applications such as artificial intelligence and high-performance computing. However, higher bandwidth requires higher memory access per. Therefore, HBM has been introduced, but uh, 2D transmission on silicon interposer prevents improvement of access energy. To solve this, heterogeneous 3D integration is proposed. For heterogeneous 3D integration, there are two approaches. One is memories on top of XPU, and the other is an XPU on top of memories. The issue of left type is cooling. Since memories are on the top, the XPU cannot dissipate heat efficiently. The issue of right type is per delivery. The impedance of TSV causes supply voltage drop and large loop. BBCube 3D has dense TSVs and thin dies. Therefore, it has the potential to solve these issues. In BBCube, two types of stacking processes are employed, chip-on-wafer and wafer-on-wafer. XPU stacked with chip-on-wafer. First, XPU dies are attached face down on a waffle-shaped wafer. Next, the wafer is bonded on XPU or DRAM wafer and thin to about 10 micron. Then, through silicon view are formed and connected to XPU or DRAM on the lower wafer. DRAMs are stacked with wafer-on-wafer process. First, a DRAM wafer is bonded onto a carrier wafer and thin. Next, it is bonded on the other XPU or DRAM wafer, and the carrier wafer is debonded. Then through silicon via are formed and connected to XPU or DRAM on the lower wafer. We are confirming the wall and curve process. Same image of the resulting curve and wall structures are shown here. BBCube has two Spal features. One is bumpless view-last interconnect similar to kappa local backend of line. In BBCube, stacking and thinning is first. TSV formation is last. Wafer or dies bonded on using SiO2 adhesives. Therefore, nanoscale planarization like hybrid bonding is not needed. Moreover, backend of line-based process result in high reliability with low thermal budget. The other is ultra-thinning. The aspect ratio of the TSV is reduced to about 2.5. Therefore, BBCube can realize a low-cost interconnect compared to conventional 3DI using micro bumps and hybrid bonding. High density, low capacitance, and low thermal resistance TSV can be realized with BBCube. The TSV pitch of BBCube can be narrowed to 10 microns, so the density of TSVs becomes 16 times higher than conventional 3D integration. Due to short and slim TSV, the TSV parasitic capacitance of BBCube becomes 1/20 that of conventional 3DI. In addition, due to direct copper-to-copper contacts and thin bonding layer, TSV thermal resistance of BBCube reaches 1/70 that of conventional 3DI. We calculated the power supply impedance of XPU on the top of 8 laminated DRAMs. The power supply impedance of BBCube becomes 22 times lower at 10 MHz and 220 times lower at 5 GHz in comparison with conventional 3DI. When 40-watt XPU is stacked on 8 laminated DRAMs, the DC drop at XPU is only 2.9 mV in comparison with 65.1 mV in conventional 3DI. Next, we analyze the temperature in the laminated DRAMs. Maximum temperature of DRAM should be under 85 degrees C to maintain its refresh interval of 64 milliseconds. In the case where the DRAM are on top of the XPU's heat is dissipated through the DRAM. So, in conventional 3DI, the acceptable XPU power is only 12 watts. In BBCube, XPU power can be increased to 30 watts. In the case where the XPU are on top of the DRAM, the XPU are cooled directly. Therefore, in BBCube, XPU power can be increased to 47 watts. Finally, we calculated the bit access energy of DDR5, HBM2E, and BBCube 3D. The example of HBM's access route is shown here. The bit access energy includes low activation, bit line pre-charge, and data transfer within the DRAM die, within the TSV, on a sequence interposer, and within the XPU between memory controller and last level cache. The results are shown here. BBCube reaches a bandwidth 30 times higher than DDR5 and 4 times higher than HBM2E with a bit access energy 1/20th that of DDR5 and 1/5th that of HBM2E. The breakdown of the bit access energy is shown here. For ease of comparison, BBCube is said to have the same bandwidth as HBM2E. The fine-grained DRAM design gives BBCube low access energy, but more notably, data transmission energy becomes extremely low compared with HBM2E. Therefore, even if the bandwidth is made 4 times higher, the power consumption of BBCube is lower than HBM2E. In the HBM2E system, the power consumption of memory access is expected to account for up to 40% of the total system. When BBCube 3D is used, it can be reduced to 8%. Thank you for your attention.
Any questions? So, yeah.
Hi, great talk. I was going to say, can this technology be made non-volatile as well? Or?
Yes, memory is both volatile memory or non-volatile, both is useful.
Thanks.
Any other questions? So I've got one. If the HBM2E has been out for a while, and HBM3, several variants are on their way, how would you compare yourself to HBM3?
I think BBCube is available more high density TSV, like now 10 micron pitch, but 5 micron or 2 micron is available, I think. So bandwidth is can increase more.
So HBM3 is going to have more width, but since yours is dense, if you went wider, you would go up just like they do. I see. Any other questions? Okay. Let's thank our speaker.